I don't forget. All right. All right. So I'm going to get the class started. We are going to have exam two um, more than a week away. Okay. The reason is next. Let me make sure my mic is the right place. So the reason why, we are going to have our exam on the Tuesday after next Tuesday is because next Thursday I have interviews. I'm one of the interviewers on the panel, so I cannot, have a class or have the exam. So you guys can kind of push the exam to the next Tuesday. So let me go take a look at the calendar. So this way we know for sure, which day we are talking about. So if I go to the calendar, which takes a lot of time and don't know why, but that's not an abnormal. All right, so today is the 6th. Originally, I have the exam, scheduled on the 13th, but because of an interview that I have to be a part of, so we're moving the exam to the 18th. Okay, so I will put an entry over there. Okay, so on the 18th, this is going to be exam 2 of CISP 310. And the start time is the beginning time of the lecture itself, which is 9 o'clock a.m. And then the end time is 10:20 a.m. And that's it. Okay, so I'm just gonna submit. So this way it is on the calendar. It's on the 18th. All right. So with that said, we are going to go over the exam or the exam from last semester. Yes. So we do have class next Tuesday, but not next Thursday. Hmm? The, oh, is it? Oh, it's on the Tuesday? Oh, that is not good. That is not good. That means we're not going to meet for a whole week. How am I going to cover all the topics? Okay, well, in that case, it doesn't impact the scheduling of exam two. We are still going to have exam two on the Tuesday after next Tuesday, which is the 18th. So I won't be seeing you guys until exam two. Because we have Veterans Day on Tuesday, and then I have interviews on Thursday. So that means the entire next week, I won't, this class has no meeting for the entire week next week, which is not good. I might make some videos, just so that you guys can watch it to kind of keep the engine warm. And if you have questions about the exam, you can always kind of email me too. All right. Yeah, I don't keep track of holidays and days off. All right, so this is exam two from spring 2025, and that's what we are going to go over first today. And it's just a PDF, download it, and then I can show you the PDF itself. All right. So the first question is a PDNC kind of question. And it is really hard to track, when I'm using a PDF for this particular one. So I have prepared a spreadsheet just for that. Okay, because in the class it's easier to use a spreadsheet, and this is all you need. Okay, even though there are some descriptions and whatnot, but this is actually all we need. So let me first explain what the numbers are, and also we'll go ahead and magnify this a little bit, at least at the beginning, just so that we know, how the spreadsheet is set up. So when you look at the digits here, the numbers. The numbers are indicating their node numbers. Okay, so each um, for columns that share the same number, they are on the same node. They are electrically connected. Are we understanding that concept? Okay. So it basically means, if you were to draw the picture, they would be wired together. Okay. If they have the same number. I'll give you an example. So let's pick number five, node number five. So node number five means this, whatever this port is connected to this port. And I think there's one more. So these three ports are connected. So now the question is, what are those things that are connected? The second thing is NAND, which means it's the name of the device itself. And then there might be multiple devices of the same kind. So this is NAND gate A, this is NAND gate B, and so on. And this is the input 0 of NAND gate A. This is input 1 of NAND gate A. Are we doing okay so far? That's pretty much the same notation that I also used in class when we first talked about the SR latch. So you might want to kind of go back to the SR latch discussion. It is basically essentially the same method in that class. Any questions? Okay, so let me go. Are we okay with node numbers? Okay, node number five, it has three things connecting, and then I'll pick another example just to be sure. Okay, so let's take a look at node number 10. So node number 10 only connects two ports together. Okay, so those are the only two being connected by node 10, and then node 8 is here. It is also here, and I think that's it. So node 8 only connects these two together. Okay, so now we move on to all the B's, right? So all three columns here, they all belong to device B. Device B, which is indicated by the letter, they're basically indicating these are ports of the same NAND gate. And because it is a two input NAND gate, there are two input ports and one single output port. It is exactly the same format as when we did the PDNC lab, and also when I explained the SR latch in class. Okay, except this one is a little bit bigger, a little bit more complex, but it is essentially the same thing. So I'll be feeling okay in terms of yes. No, it's given to you. Yep, yep. So the table is given to you, except in the exam itself. Okay, well that tells me that someone has not opened up the exam from previous semester. So this is actually given to you, along with some of the cells already filled in. So your job is to fill in the ones that are missing. Okay, but I'm not telling you which ones are missing. You're supposed to find them. All right. So are we doing okay so far in terms of what the activity or what the question is asking you to do? All right. So as we do it, I think you'll get a better idea of how to do this one. All right. It uses the same standard as in class. Anything that is boldface, like these two, indicates they are changes from the outside because you can see how these are changes to ports of an input pin. And because this is an NC row, we are propagating the zeros and ones to everything of the same node. So this is node 0. So that means that I need to update all the node zeros to a 1. So you just have to scan. Here's another node 0, and here's another node 0. So that's why this one using the NC is propagating to column P and also column G in this case. The other input pin that is changed, which is also boldface, is this one here. This is node number 1. So now we look at all the node number 1s. Make sure that you don't accidentally miss something. So these are all node number 1s, and obviously we are missing one of them here. So that's part of what I'm asking, is for you to fill in the ones that are missing. Are we good so far? So I'm using a red color here just so that what I put in as part of the answer stands out compared to what the question is providing to you. Are we good so far? Okay, we see nods. Okay, good. So now we move on to the second row, which is a PD row. So a PD row is essentially, PD stands for propagational delay. So that means based on the changes to the input ports of the previous row, what output is changed as a result. That's what a PD row is trying to reflect. So now you look at this one here, it is changing one of the inputs of the NAND gate F in this case. It is changing something from unknown to a 1, but this one is still unknown, so that means the output is still unknown, which is not a change of state, so we leave this one blank. This 0 here is going to input 0 of a NOT gate C, but because this is a NOT gate, it only has one single input pin or one input port, so the output port is guaranteed to be a 1 in this case. This 0 is going into one of the two input ports of an AND gate, not a NAND gate. This is a regular AND without the negation. So the output is also guaranteed to be a 0 here. This one is already done because this is the input of a NOT gate. The output is going, if the input is a 1, the output is going to be a 0. These two are corresponding to input pins, so they don't have an output anyway, so there's nothing to do with these two. So are we doing okay so far in terms of the three cells that I just filled in? So we're good. All right. So now we move on to the ANSI row. So the ANSI row is looking at the previous row and ask, okay, do we have updates? Yes, we have three updates. So now we look at node 2, which got changed to a 1 from the previous row. So now all the node 2 would be changed to a 1. So I think that's only one up to here. This one has to be changed to a 1 because of this one over here. So I just have to scan the numbers, to make sure that I don't miss another 2. Okay, so these are all good. There's a 0 here that got changed, so all the node 5s need to change. This one is already done, this one is already done, and I think that's it. So we are good. And then this is node 6, so we have to change all the node 6. So this one is already done, and I'm just scanning the numbers, make sure I don't miss any 6s. All right, so we are good here. So when we're done with the NC, we go to the next row, which is again a PD. So this PD is doing exactly the same thing. It's looking at the previous row and ask what devices have the input ports changed, and is the output going to change as a result? So in the previous row, we can see that with NAND gate A, both input ports become zeros. So the output is going to be guaranteed to be a 1, but this is provided to you. This is in the question itself, is already filled in. This one is for NAND gate F. NAND gate F already had input 0 being a 1 before, but that does not guarantee the output in any way. But once we change the other input port to a 1, then we know the output has to be a 1, so this one is already done for you. And that concludes this particular row, I believe. Oh, wait, I forgot about this one here. So this one is a NOT gate. Device J is a NOT gate. The input is changed to a 1 from the previous ANSI row, so the output is going to be a 0 for this particular row. So are we good so far? Okay, so it's a little bit on the tedious side, but it's not insanely difficult. Um, and now we're getting onto the next ANSI row. So that means I just have to look at all the port 3s, make sure they're all zeros. Okay, so that's one, scanning, and we don't have any more port 3s. And then we look at port 7, I mean node 7, and there's a node 7 over here, and I think that's it. Okay, there we go. And then we have a node 8, and node 8 has one over here, and I believe that is it. So this NC row is also done for at this point. So with this row also done, we move on to the next PD row. The one of the input port of a NAND gate is a 1, the other one is unknown. The output is not known because this doesn't give us any clue of what the output is supposed to be. And then with this one, it is a NAND gate again, and only one part of the NAND gate is known to be a 1, so the output cannot be known. So this particular PD is It's not supposed to be empty. Okay, so I made a mistake somewhere. So the question is, how can I tell that I made a mistake? I know I made a mistake because this row is not supposed to be empty. It's not supposed to be a steady state because you see how this one is bold-faced? That is the next transition of the input ports. So um, so that means the current cycle is not supposed to be done until this PD row is empty. So that means this PD row being empty means that I missed something. So now the question is, how do I figure out what I missed? Um, so the way I can tell what I missed is actually easy. I look at the following NC row, look at this next NC row here, and we see that that NC row reports the node 4 is supposed to be changed. So now I look at the other node 4, which is out here. Aha, okay. So that means there's supposed to be a 1 over here. Okay, let me just kind of pause and see if you guys understand what I just said. I performed a self-diagnosis, okay? I detected a problem, okay? And I said, okay, I must have made a mistake somewhere, okay? The realization that there's a problem is because I have a row 7, that is not supposed to be empty, okay? I know it's not supposed to be empty because we should only arrive to a steady state where the PD row is empty right before a row that has either um, one of the two input ports being bold-faced, but because of my mistake, row 7 was also empty. So that does not make sense, okay? It does not make sense that you have a PD row that that is empty, and yet the following NC row has some entry in it. That does not make sense. Yes. Um, I personally prefer to go forward, but this helps me catch problems. Yep. So you can use this kind of like to catch a problem. Is like um, you can go backwards that way. Yep. So now I know that I missed this one over here. Okay, so I caught my own mistake. So there we go. Okay, so this makes sense, right? Because there's a 0 here. The 0 goes into the input of a NOT gate, so the output should become a 1. All right, so that one explains this one over here. And then the next PD row is empty, okay? But we want to double check whether it should be empty or not. In other words, we look at this one here and ask, does that change the output of AND gate P? Well, no, it should not really change the output of AND gate P because we now know that the first input is a 0, the second input is a 0. I take it back. The first input is a 1, the second input is a 0, but the output continued to be a 0. That makes sense. You're turning your head. Uh, are we okay? We get okay. And that's the only change. So that means this PD row being empty makes sense. So now we move on to row 10. So row 10 with a bold-faced 1 means this particular input is changed from the outside. So the job of the NC row is to propagate this particular one to everything that connects to node 1. So I think this is the only one. Oh, there's one more over here. This is also node 1. So in this particular version of the test, if a column is not filled, it is not filled for the entire column. So that means we have to make sure that it is also filled in now at this point. So we put the one over here. All right, so after that, the reason why I put everything into a spreadsheet is so that we can do this. So I can scroll, the bottom part without changing the top part. All right, so we are now onto the PD row. So we have to examine. This is a NOT gate. The input was changed to a 1, so the output is guaranteed to change to a 0. This is a AND gate. So now that we know both of the inputs of the AND gate P are 1s, the output should be a 1. But I have to make sure that it doesn't have a 1 already. It had a 0 at this point. So since it had a 0, now it becomes a, oh, okay, not Not on this cell. This is the wrong cell to do it. Okay, undo, put it on here. There we go. And now we move on to this one. This is also oh, this is an input pin, so it doesn't have output, so we are done on this PD row. So now we look at port 2, and we need to update everything else that connect to port 2 to a 0. So this is 1, the other one is over here. So now we have to make sure that this one is also updated to a 0. I think those are the only two connected to node 2. This is node 5, so we have to locate all the node 5. There's one here, there's one here. So I think everything is accounted for. And now we move on to the next PD row. So now we have one input of NAND gate A being a 1. And I kind of have to scroll back to see what the other one is. The other one was a 0. The output was already a 1, so that is not changed. With this one, it is changed because what we had before was a 0, which guaranteed the output to be a 1. But the other input, the first input of NAND gate F, is a 1 already. So now we have 1, 1 as both inputs of NAND gate F. So the output is now a 0. So that makes sense. Okay, so we are moving on to this 0 here. So this 0 is going into the only input of NOT gate J, so the output is guaranteed to change to a 1 over here. So now the next one is the NC, so we just have to do the propagation, making sure everything that connects to node 3 are updated. So the one is right next to it. And I'm just scanning the numbers here to make sure that we don't see any other node 3. So that's it. This is a node 7, and the other node 7 is here, but I need to make sure that I'm not missing any other node 7s. I think we are not missing anything. So when we scroll down, we have a PD here that is now empty. Um, oh, okay. We put a 1 here. So this one, okay. So this row is done, and now we move on to this row. Now that we have the first input of NAND gate K being a 0, and we'll see whether it already had an output. Nope, it does not have a specified output. So that means the output is guaranteed to be a 1 at this point. And then the output of this NOT gate is guaranteed to be a 0 at this point. So those are the only two that I updated this time. This is node 9. I need to update all the node 9s to a 1. So that is updated here. So that's good. Accounted for. This is node 4. I have to update all the node 4s to zeros, and that's the only other node 4, so we're good here. And then we move on to the next row, which is a PD. So now we look at NAND gate B, and we need to take a look up here. So both inputs are 1s now, which means we now know the output of this NAND gate is going to be a 0. And with this particular 0, it is going to NAND gate P. So we should guarantee an output of 1 here. But if it's already a 1, then it's not an update, and we don't put anything there because it's already a 1. Oh, wait. Okay, I take it back. It's a regular AND gate, it's not a NAND gate. So that means that we do have a change to 0 from a 1 over here because it had an output of 1 previously. So now it is updated to a 0. So that should be done with the PD, and now we move on to the NC again. So this 0 is at node 10, so we need to update all the other node 10s to a 0, so that's accounted for, so we are all good. This 0 is on node 5, and these two are the node 5s, so everything is accounted for with the NC. So now we move on to another PD again. um, This 0 is going to one of the two inputs of a NAND gate, which means the output should now be a 1. But if it was a 1 already, we don't put a 1 here. So we have to kind of scroll up. It's already a 1, so we do not put a 1 over here. This is a 0 going into, but this is already updated to be a 1, so we are all good there. This is also a 0, which means this output should be a 1, but we only put a 1 here if it is not already updated. So we have to kind of go up. It is already a 1. So that means this PD row is all done. And now we go for the another NC, and this is node 7. Everything that connects to node 7 should become a 1. That's the only one that connects to node 7. Now it is a 1, so this NC row is all done. And then the next one is empty because we can always double check to see whether it should be empty or not. So we have a 1 and input port changed to a 1 with NAND gate K, but since the other input is still a 0, so the output should still be a 1. So we'll double check, make sure that it was a 1 already. Yep, it was. So that means this PD row being empty is also correct. And now we move on to this row. There's a boldface 0 here, which means this is the only change from outside. It is to node 0. This is also node 0. It gets a 0. This is also node 0. It also gets a 0. So everything is accounted for. On to the next row. Um, because NAND gate F already had one of the input pins being a 0, it continues to be a 0. The output was a 1 already, so it's not a change to a 1, so we don't put anything here. This one is already accounted for, so we don't have to deal with it. So the only one that we have to look at is this one, but since it belongs to an input pin, so it doesn't have a corresponding output, so that's all we need to do. So this is the only change from the PD row. It is on node 6. So on the next NC row, we update everything connected to node 6 to a 1. So this is the only one. And then we move on to the next PD row. And this one is not changing the output of the NAND gate because of this particular 0. We already know the NAND gate has had an output of 1 already. So we just scroll up to be sure. Okay, yep. So there's a 1 already. So that means there's nothing to do on the row that we were on. And I have completely lost track of which one I was talking about. Yeah. So which row? Row 20. Oh, okay. Yeah, I have the highlight here, so I still have the quote-unquote cursor. Okay. So that means it's all accounted for, and that's the end of the trace. So it's a little bit tedious, okay, but I set it up this way so that you can get partial credit. Okay, if I just leave the whole thing blank and have you guys to fill in, if you make a mistake somewhere, it can propagate and mess up everything after that. So if I set it up like this, then if something is conflicting, like you think it should be changed, but it's not a change, or something is conflicting with whatever is given to you, then you have a quote unquote checksum. Okay, you can go and you can say that, okay, something is not right, and do the diagnosis like what I just did, and kind of go backwards and go like, okay, where did I make a mistake? Are we good so far? So I think this is a relatively gentle way to kind of work on this kind of question instead of me filling in all of these values already and just say that 5 of these are wrong somewhere. That would be a little bit more brutal. I think this one is not as brutal. So are we good? All right. So that's question number 1, and we are moving on to question number 2. All right, so this is question number 2. You are given the opcode 5D in hexadecimal. So it is broken up into multiple parts. Taking into consideration of opcode hijacking, figure out the mnemonic of the given opcode. So the key here is, what is the mnemonic? Which column of the opcode table is the mnemonic? Just offhand, you should know that already. We have been looking at the opcode table so often. So which column of the opcode table gives you the mnemonic? Some people have a loud voice, I don't. Okay, column B. Yes, that is correct. It is column B. So you just have to match the pattern, okay? So the first thing you need to do is to convert the 5D into binary, which is 0101, 1101, and then you look up the opcode table. So you look up the opcode table, the opcode is in column A, so you try to make a match and go like, okay, which row is corresponding to 0101, 1101? Ah, this is the only row. So it's a CPR instruction of some kind. But we also know that XX is 1, 1 and YY is 0, 1. So when you look up here, we know that register X is actually register D, and then register Y is register B. So that's how we can tell, from this analysis that the instruction here, I can actually just put the answer here too. Oh, that's not what I want to do. I want to type over. Um, okay, this is what I'll do. I'm going to use an editor on the side and to record the answer. So this way it will be on it will be recorded. So let me start up mouse pad and click yes. There we go. Move this one out the screen and then start a new document here. There we go. So I'm just going to use mouse pad to record the answer. This is for question number 2, part 1. So the answer to that part is going to be CPRDB. So do we have any questions about why the answer to part 1 is CPRDB? So you have to specify the registers, okay? Because the code that I gave you already indicates the registers. So now you kind of have to think about, okay, in order to answer this question, what do you need to bring with you? What do you think? The opcode table and yep, the hexadecimal to binary conversion table. That would be handy to have. Okay, so I cannot remember the opcode myself. Okay, so I need the opcode table to answer this question, but the hexadecimal to binary conversion I can do that in my head. So for me, it's just the opcode table. So so remind yourself, okay, from this experience, remind yourself what you need to bring to help you answer the questions. Okay, because I cannot give you any additional material during the exam. It is open book and open notes. So the responsibility to bring enough information with you is on you. Are we doing okay? All right. All right. So this is part 1. And then we look at part 2. Okay. Question 2, part 2 is asking what is the RTL corresponding to the mnemonic of the previous part. Okay. I'm going to make a statement. I will not answer questions about what is RTL because we have talked about it so many times already. What is RTL? Register Transfer Language. That is correct. So which column of the opcode table gives you the RTL? Column C, very good. Okay, so if you look up column C, it is going to basically specify register D gets the value of register B with no parentheses or asterisks anywhere. Okay, we're just copying the value of the register here without dereferencing. All right, so we move on to question number 2, part 3. So this one starts to get a little bit more complex. Okay, it is asking you specify all the necessary endpoints, ports, connections of components to implement the answer of the previous part, which is part 2. For example, the instruction fetch cycle can be described as instruction register.d gets ram.d. So that means whatever RAM is outputting in the read cycle is used to update the instruction register because the input of a register is port D, and that's why we specify port D. Also, at the same time, in order to address the correct location, the A port of RAM should connect to the Q port, which is the output of the program counter. So I'm using that as an example, okay, to illustrate what type of answer I'm expecting. Each endpoint should be the name of a component dot the port destination. So you name the component and then you use a dot, just like object-oriented programming, to specify which port we're specifying. You can use reg A to refer to register A in the register bank, etc. Okay. So now that we know that we eventually all we want to do is to update register D to be the same value of register B. So the port connection is going to be specified as register D's D port gets the Q port of register B. So writing this down may not be very helpful because you're guaranteed not to get the same question. So the key here is to understand the scope, what you need to answer the question, what you need to bring with you to answer the questions. Those are much more important than the answers themselves. Okay. Besides, the lecture is getting recorded. Just double checking. Yes, it is being recorded. So the scope, how to answer the questions, what material you might need to bring to answer the questions, those are far more important than the actual answer that I'm giving you right now. So I'm going through the process to illustrate the reasoning, the material, where they're coming from, and how to get to the answer. That's the important part. The actual answer is not nearly as important. All right, so we move on to part four. All right, so part four in this particular exam says you'll fill in the following part. Oh, this is this is where it gets a little bit hairy. The value of each entry should specify in base 10 or use a single question mark to indicate the value of the entry does not matter. For entries that are relevant to part 2 and 3, briefly explain the value. For example, does the entry enables or disable a certain component based on whether it participates in the operation? Does the entry configure a component for a specific mode of operation? Or what endpoint from part 3 does the entry help route? Okay, so that has to do with multiplexers and demultiplexers. The explanation carries 50% of the points, which means people who only give me the correct values will only get 50% of the points. All right, your answer should make sure the processor performs the specified operation of the given opcode correctly and safely. All right, so we are going to go through this and figure out how to answer this question. So we have to basically give each one a particular value, can be potentially a question mark, and a brief explanation. So are we understanding what the question is asking? All right. So the way I can try to do this is to just kind of copy and paste this into Mousepad. Hopefully the line feed is preserved. Excellent, it is preserved. So the next thing we need to do is the map of the processor. And one was provided last semester, okay? But it's the plain vanilla one where things are a little bit small and nothing is highlighted. Okay. So if you guys had done what I have recommended, which is highlighting using different colors and so on and so forth, you might want to bring your own. Okay. Because this one is just black and white, plain vanilla. There's nothing fancy here. Okay, so if you have already highlighted your own, annotated anything, you can bring your own. Okay, you can bring as much material as you want, as long as it is printed on paper or handwritten. Okay, so from this picture, it actually does give me everything that I need to answer the question. It's just a little bit harder to find. So what I need to do is to get here first. This is the register bank. So I need to somehow route register B out of the register bank and then route it back into the input of the register bank in order to update register D. So the first thing I can tell is, okay, register D is right here. So I know register input select needs to be a 1 1 or a 3. And we also know that input enable is going to be a 1. So if I go back to the main diagram here, I know this is hard to read. Okay, we can magnify a little bit. So we know RISEL needs to be a 3. Okay, so we'll go ahead and specify this to be a 3 to select register D to update. We know RIEN has to be a 1 to enable a register to get updated. Okay, so you guys cannot see what I just typed here, but I kind of verbally say out here what I was typing. All right, so that's good. So now the next question is RI mux. Okay, how should that be connected? So it only has two modes, okay? So this is, the input one or input zero. We'll work with input zero first. Input zero goes all the way to the RAM D port, which is not what we need. Input one is what we need. So RI mux needs to be a one, okay? So it needs to be a one to route from, um, so you can actually see how it is routed. Uh, mm, nope, I take it back. I take it back. It should be a zero. My mistake. Okay. So it has to be a zero to route from um, out zero of the register bank. Now, your explanation doesn't have to be exactly like that. You just have to kind of tell me what it is. The other way to do this is you can just say that, which route that we have already talked about in the previous part we are talking about. So that's the other way to do it. I think it is a more concise way to do it. So all you need to do in that case is really just to explain they're all a part to make this happen. Okay, so that makes it a little bit easier, right? For this particular operation. So you can just do that part here. There we go. RAM load is going to be whatever does not matter because RAM cell is going to be a zero, okay, not used. So that's why this one no need to specify, no need to specify. And you can basically use a short form so it's easier for you to hand write, okay? Okay, so now we look at RI0EN, which is here. So that needs to be a 1. Okay, so this is part of the route of what we need here. And then RI0 cell, which is selecting which register is routed to register output 0. That would be also 1. Okay, and that's also part of what we're trying to do here. RO0 demux, which is this one here. So now we have to be careful because we need to make sure that we select. Okay, I need to follow the arrows here. No, that one. It is that one. Mm, Hmm. Is it out one? Okay, so out one goes here, and that goes to the address port. I think it's 0, but I just need to find out. Yep. Okay, it just goes around. Okay, let me trust that route again. Okay, so it is here, go all the way over here, all the way down, all the way back here, and then up. So it is output 2 of this demultiplexer. So that means, RO0 demux needs to be a 2. Poof. I don't know about you, but when I was a child, I did a lot of puzzles, like mazes. So you have a mouse on one side and you have the cheese, somewhere else in the maze, and then you have to find the route to do it. Who would have known that that would actually be helpful later on in my career? I also did a lot of pictures, like you're given two pictures and you're asked to note the differences between the two pictures. I did a lot of those too. That turns out to be really helpful in programming because it helps with abstraction. You're looking for what is common and what is different between two things, which is actually what programming is about. All right. Okay. So RO0 cell is a question mark because it is not used. And RO0 demux, you have to be a little bit careful with that one, I think. So that one can be anything, can be question mark because it is also not used. ALUEN has to be a 0 because the ALU is not used and we don't want to power that thing up if it is not used. The operation is not used. ADDR is a question mark because we are not using RAM. If you're not using RAM, then we don't need to specify what goes to the address port of that RAM. PC is also going to be not used because we are not changing the program counter in any way, and PC is only useful if you need to change the program counter. And this one is important. Turn it off, okay? Because we don't want to accidentally update the program counter. So now it's up to, now we have these three leftovers. So those three leftovers have no names because that's the way they look like when they're coming out of the ROM component. So when we look at the ROM component, which is this one here, this is 0. And 0 is only useful for enabling the instruction register, which really should be enabled only when you're fetching. So we should put that as a 0 because we don't want to update the instruction register. Now, if you put a 1 here, it is not exactly wrong. You'll be updating the instruction register. You might end up, doing something to it, but it is not super duper important. So a 0 or question mark would be okay, but a 0 is preferred. All right, 24. So 24 is coming straight out of the splitter here. So 24 goes all the way to this selector here. And at that point, we don't want to change, the microcode pointer is not going to change, but it will change in the falling edge. So that means we need to maintain it to be a 0 because we want to keep it in a decode cycle instead of incrementing it. Wait, we want to increment, so we want a 1. Sorry, I take it back. So we want a 1 over here, and this one we need it to be a 0 because otherwise it's going to reset the microcode pointer because that's what bit 24 is. Bit 24 goes, no, 25, sorry. So bit 25 goes to one of the inputs of the OR gate, which then goes into the reset pin of the register. So if bit 25 is a 1, then we would have reset the register itself, the microcode pointer register, which is not good. So that would be the answer, okay, with some explanation. All right. So how do we prepare for a question like this? Yep. And we did that a few times in the class, and I made a recommendation that you guys should do several exercises, pick some instructions that we haven't talked about, and look at how things are configured when we are in the execution phase of an instruction. That's exactly why I told you to do that. All right. It is not too late, especially for this class, because your exam is on the 18th. Today is the 6th, so you have what, 12 days? So I'm going to say you have 11 days to procrastinate and 1 day to study, which usually is how it turns out. Okay. Now, do I recommend doing that? No, but my own children do that a lot. So I understand if if people procrastinate, because I procrastinate a lot too. The question is, do you survive your own procrastination? Are we good so far? All right. So, do we know how to study? Do we know how to prepare for the exam, knowing that this is the scope of the exam? So, we have some idea. Okay. So, if you want to look at, if you look at this map that I have here and go like, this is awful. Okay. I don't like the way, things are represented here. I would much rather prefer to have color coded all the nodes, all the important ones anyway. Go do it. Okay, color code things, make annotations, blow it up on a bigger piece of paper if you have access to a larger printer. Um, do whatever you need, okay, so that you can help yourself in the exam. Okay, it's just that you cannot use electronics, but you can still do a lot on paper. Are we good so far? Cool. All right, so that's part number 4. I believe that was the last part, but I could be wrong. Let me double check. Huh? No, we don't have the ASM question anymore because we still have to go back to floating point numbers. Yeah, for this class, we did not have floating point numbers in the first exam. In the previous semester, I did floating point. Yep, yep. And we're going to take a look at that example. All right. So now we are going to take a look at floating point numbers. Okay, so that would be CISP 310, the previous semester. This is exam 2. Oh, exam 1, because it's from the previous exam. And I'm going to pick version 00. So the third question, or the fourth question, sorry, the fourth question from the previous semester. So I'm going to use this one as an example. So once again, it is not about writing the answers to this specific question. It is knowing the scope and also what content you need to understand in a very thorough way in order to answer the questions. Okay, so that's the important part. Even though I gave the class, the definition of VD, you might still want to have it in your own notes, okay, just in case, right? Because this is important. The entire way that a double is encoding a value is expressed by VD. Now, it is only useful if you know how to read it, okay, so you have to first make sure that you know how to read it. This is exactly the same definition that I used when we talked about the double, the IEEE double precision floating point number. Okay, that's exactly what I used when we talked about that topic. So it is not new. Okay, this is really a repetition that I pulled out of my own notes and stick it into the exam. Okay, all right. So let's go ahead and answer the questions one by one. And for this one, I will try. Not sure whether that's going to work. Let's not do that. Okay, so I'm gonna keep the same approach, which is using my mouse pad here to record the answer. All right, so this is a Q3. I call it Q3. Dot one. Step by step, show the value of z represented by the base 10 decimal number. Okay, so the key here is step by step. So I have had many people who just gave me an answer. Okay, so if people do that, they get at the most half the points. Okay, so if I ask for step by step, you have to show me how it is calculated. So the question is, to what kind of detail do you want me to show you? Well, at least show me how you do the base conversion. Okay, so the way I would do this one, but this is just me. The way I would do it is I would convert the base 2 number to a more friendly version before I do the actual base conversion. Okay, but you don't have to do it that way if you want to kind of deal with small um, negative powers of 2, that works too. So I'm gonna just go like, okay, I'll do it really, really step by step for the first step. So what I'm doing is I'm using the power of 2 to move the decimal point or binary point in this case. So now I can go like dot dot dot, and then eventually we get to 1 1 0 1 0 0, and then point 0 1 in base 2 times 2 to the power of 0. Okay, so I'm just going to pause here and see if there are any questions. Okay, let me move that part up so that people in the back can see it too. There we go. All right. So do we have any questions about the steps that I have shown here? All I'm doing is moving the binary point because I can afford to do it because I can reduce the power of 2 that I multiplied to the mantissa, to the original mantissa. So once I've done that, I now I do the conversion. Okay, so I look at this and I go like, okay, so what is this one representing? So we just have to count the digits. We have 1, 2, 4. So we have 1, 4, 8, no 8. We have 116, and then we have 132. And then we have no halves, but we have a quarter. Okay, and then we multiply this by basically 1 because 2 to the power of 0 is 1. And now I just add them up together. That would be 52, I think, 52.25. Okay. So if you think you need a calculator to do this, go ahead, bring your calculator. I will not laugh. Okay. But for something like this, I would just do it by hand. Okay. Because by the time I pull out my calculator, it's already done. And besides, you have to show the math, right? So by the time you have to show the math at least up to this point. So that means by this point, what is left is arithmetics. Okay. So, but I understand. Okay, I was just teasing about the calculator thing. So bring your calculator with you, and just be sure. But for this kind of math, you don't even need a scientific calculator. So if you have one of those freebies from a trade show or something, those will work just fine too. All right, so that's part one. And now we move on to part two. So part two is saying, okay, we have to compute the biased exponent of 2 and represent it as a base 10 number and explain your answer. Okay, the bias is 1023. So the biased exponent g equals to the original power of 2, which is 5, plus the bias amount. So that would be 1028. And if anyone is thinking, but Tech, how are we supposed to know the bias? I'm going to go like, I cannot answer that question. Well, in the exam, I for sure cannot answer that question, but right now, I hesitate to answer the question. I'll let you guys answer the question. So, if you completely have forgotten what is the bias of an IEEE double precision floating point number, can you still figure out the bias amount from the exam question itself? Yep, right there. Okay. So there you go. So that's number two. And then we go to number three and convert G to a binary number. So the conversion process, you can do the formal thing, you can do the easy way. You just have to explain to me that you know how to do the conversion. Okay. So the way I would do it is 1023 is 1024 plus 4. And then 1024 is 1 followed by 10 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in base 2, and then 4 itself is 100 in base 2, like so, and then we just combine the two. Okay, the way I would combine it, if I don't have to handwrite, okay, you guys unfortunately have to handwrite this, is to turn that 0 to a 1, and we're done. So this is my way of showing steps, okay, showing how to do the conversion. All right, so we move on to part number 4. So let's see what part number 4 is asking. Okay, there we go. Okay, part number 4 says, assemble all the bits of a double x such that, VD of x equals to z. So x itself is really just a 64-bit pattern, okay? It is not the value it is representing, it's just a bit pattern. So we specify, bit 63 is a 0 because because z is non-negative. Oops, I mistyped here. It is supposed to be a 0, not a 3. There we go. And then bit 62 down to bit 52 is the biased exponent, which is 1 followed by what, 7 zeros? Yep, 1, 2, 3, 4, 5, 6, 7, 1, 0, 0. Okay. And then bit 51 down to 0 would be the fractional part of the mantissa. So that's going to be 101, 0001, and then a whole bunch of zeros. Okay, so now I have to specify, what I mean by a whole bunch of zeros. So, I'm just approximating what you can do with handwriting. Okay, so the number of zeros here would be how many? There are supposed to be 52 digits for the fractional part of the mantissa, and this part here is already dealing with 7 of those. So 52 minus 7 is 45. So we're just going to say 45 zeros. Okay? Unless you really feel like writing out all the zeros. in which case I have to count the zeros too. Remember, yes. Remember, if you spend the time to write something, I have to spend the time to read it too. This is not one of those exams where, the professor goes like, you know what? I'm gonna use ChatGPT to grade all the exams. Nope, everything is hand graded in this class. All right. So that's so now we assemble everything. Okay, we explain all the components. We just have to assemble everything. So we have zero, and then we have one followed by seven zeros. One, two, three, four, five, six, seven, and then 100, and then we have 101, 0001, and a bunch of zeros after that. Okay, all right. And because I already answered the question of there are 45 trailing zeros, I don't have to re-specify here. I just need it to be done once. All right, question three, part four. Oh, that's part four already. And we are now moving on to part five. No, that's part four. Did I forget something? Or did I miscount something? Oh, I forgot about part three. Okay. So Q2.3 is converting this into a. Oh, that's part three. Okay, I got part three. I just did not designate part four. That's all. Okay, this is Q3, part four. And now we can move on to part five, which is if you have the hexadecimal to binary conversion table, it's really easy. Or if you have it memorized, it is also fairly easy. So now we just have to convert it to a base 16 number, which is also known as hexadecimal. So the way I do it is to, kind of put everything back together and then chop it at, bunch, like blocks of four. Okay, so in this case, this would be a 4, and you can write it like this too, kind of really space out the thing so that everything lines up. 404A, and then the 2, and then a bunch of zeros, okay? And then the number of zeros looks like a robot face to me, two eyes and a robot mouth. But robot mouth does not look like this. I think most people do it like this. But now it looks like a skull. Mm, okay. All right, so a base 16 number to represent 64 bits needs to have 16 digits. I have 5 already specified here, so that means here we should have 11 trailing zeros as hexadecimal digits. So we'll just say there are 11 zeros here. That would be the answer to question number 3. All right. So, do we have any questions about the three types of questions? One on, analyzing the propagation inside the circuit, one that talks about the inside the processor, how instructions are implemented, and one on double precision floating point numbers. So that pretty much defines the scope of the exam. It does not tell you about the format of the questions. This is one of many formats that I can use to assess whether you understand the question, understand the material or not. Are we still doing okay? Um, so in the past, I have made it so that everything is blank. So you have to fill in the whole thing, so nothing is given to you. I can also fill in the whole thing and just say, five of those things are wrong, and then you just have to spot the ones that are wrong. Yeah. Well, alternatively, I can give you the full trace that is correct, and then you have to reverse engineer the circuit itself. It's not going to be that much of a pain because you can identify. You can probably, yeah, that would be a little bit more challenging, because it depends on how much I give you in the um, on the top, the header, right? Yep. So if I don't tell you the node numbers, which ports belong to the same node, that makes it more challenging. But with a full trace, of the propagational change, especially because of the relationship between the PD and the NC row, I think it can still be resolved. I'm gonna try that myself. before I make a decision whether that will be your question. Probably not, because I think the current format, is okay, but it's not going to be the same circuit. Okay. Yeah, it's not going to be the circuit that you're looking at, but it will be some kind of a circuit. And it's going to give you, I will give you the partially done, correctly done, trace, and you just have to kind of fill in the spots that are missing. But I won't tell you which spots are missing, but they can be implied by whatever is already in the table. All right. Yep. Yeah. Yeah, so question number two, you can practice. Okay, so what the way you practice is to just kind of pick a instruction. So I would pick from different families of instructions. Um, so the LD is one family, okay, because that's the only one that can read from RAM from a location that is pointed to by a register. So that makes it unique. So between LD and ST, if you know one, the other one is kind of just the flip side of it. So if you do one of these two, it's probably okay. But if you have time, do both. LDI, even though it seems to be related to LD, and it does relate to LD, but there's one fundamental difference between LD and LDI, and that has to do with who specifies the A port of RAM. Okay, so these two are related but distinct at the same time. I would say the difference between LD and LDI is more than the difference between LD and ST. Because between LD and ST is a direction kind of thing, okay? Which way are we going? But that's about it. Between LD and LDI is a little bit more subtle, okay? That difference is more subtle. I would look into JMPI for sure, okay? We did this in class. I believe that we did JMPI itself in class, and then pick one of the conditional ones so that you understand how the conditional branch works. So I would just pick just one of them because they all look the same. They just look at the different flag, but that's about it. And then do one with calculations. So between add and subtract, um, and okay, pick one, okay, because they kind of all work about the same way. Oh, between these, also look into CPR, but we just did CPR, so I don't think CPR is going to be too big of a concern. Um, and then we have no op and halt. That's I'm not going to ask questions about no op and halt. You know, there will be no point in doing that, right? And then there's also JMP, which is also different compared to JMPI. Okay, so they seem to do the same thing, but the way they get it done is different in a very fundamental way. Um, let's see. We have increment and decrement, but those two are not. They're not too different compared to add and subtract, but they are still kind of unique on their own. So I would pick one of these two, and then one of these two. And these three I would do kind of individually. Um, let's see, am I missing anything? Yeah, so you use Logisim in GUI mode, and then you do the Control T until it gets to the execute phase of the instruction execution cycle. Then you just look through all the tunnels, make sure that you understand. There's only one thing that you have to be careful about is the Logisim, tunnels. I cannot put a question mark to the output of ROM, so it won't tell you what is supposed to be a question mark. Like it wouldn't matter anyway. So with that one, you kind of have to think about, okay, if RAM is not enabled, if the select of RAM is a zero, then none of the control signal really matters because we are not using it at all. Or if the ALU is not used, if ALUEN is a zero, then it really doesn't matter what operation you're specifying because it's not going to do a single thing. So with those, you have to kind of think about, okay, with this operation, even though everything looks like a zero, some of those zeros should have been question marks if I could use question marks in the RAM, in the ROM, sorry, in the ROM. So does that give you guys an idea of how to prepare for the exam? Okay, very good. What about question number three? What about the floating point number question? How do you prepare for that question? Yep. That will be a very important component, and then you can just do it a few times too. I think in the class I gave you guys an example of how I went forward, starting with the value, coming up with the hexadecimal digit, and verify the actual value represented by the bit pattern. And you can try to do it the same way, okay? And then you can tweak the hexadecimal digit a little bit and then go backwards and go like, okay, this is the hexadecimal representation, but what is the interpreted value as a double? So you can go reverse, the direction too. So that's how we study for for exam number two. So are there any other questions about exam number two? Oh, one more thing. I have to change my policy about the exam. No bathroom breaks. So if anyone wants to leave the classroom, they have to turn in their test when they leave the classroom. So all that means is control your water intake shortly before the exam. Okay, and that's about it. Okay. Yes. So that's the only thing. I cannot think of anything else to add. Once again, you can bring anything on paper with you. So try to kind of make use of that availability. Okay. Typically, if I were you, I would do my own studying and then I would jot down my own notes and bring that with me, and put it on top, but I will still print out the modules, the reading, material, just as a backup. Okay. The map of the processor, the opcode table, those are all important. Um, in fact, in any class lecture, you see a screen where you go like, okay, this is what I think is important. You can always, just pause the playback, take a screenshot, print it out, bring it with you. Okay, so you have a lot of choices in terms of where to get the material to help you in the exam. You just have to prioritize because if you bring in too much stuff, you cannot find your stuff. So you don't want to bring in too much either. Okay, so bring enough, but not too much. But I don't put a limit on how much you can bring. Are we good so far? All right. So with about 8 minutes left. We can still kind of talk about coding if we don't have any more questions about exam two. So we're good. All right. Yep. Go ahead. Hmm? Yes, it's on the 18th, which is the Tuesday. Yep. Yep. All right. So if there are no questions, we are going to, in 8 minutes, we'll try to implement a program. I'm not sure whether we have talked about this one before. So I'm going to show the code to you. So uin8 underscore t will call it post add, and it will take uin8 underscore t, a pointer, uin8 underscore t, and a certain amount. Do you vaguely remember this one? So we got this one done already. Hmm, okay. Yeah, it's post add, or I probably use a different name, post ink or something like that. Yeah. So I think we did this one already. Um, yeah, if we did that one already, then you know enough to get the lab started for today already. So so we're good there. Have we done anything recursive? Okay. Okay. So that means we're ready to get started with structures. Did we get started with structures with this class? Nope. Okay, let's go ahead and do that. Um, so we'll just kind of introduce the concept first, give you a few runtime things to think about, and then we'll continue with this 2 weeks later because next Thursday we're not meeting. So the next, and then the following Tuesday is the exam. So in 2 weeks, we'll get back to this one. Oof, I don't like breaks, because it breaks the momentum of classes. All right. So what we'll do is we are going to take a quick look. We got 5 more minutes. It's more than enough time. So we'll go ahead and take a look at. So pound include stdint.h because I need control over the width of my integers. So I define x as a structure. So this is a structure definition where the first item, u in 8 underscore t, a, and u in 8 underscore t, b, and then we have a c. Okay, let's just say that's all we have. And then we have int main, and then we have a structure x, and we'll just call this var1 for variable 1. And then we'll go like var1 dot x or dot b equals to 23, return 0. So that's a pretty simple program. And then we'll go ahead and compile and run it in the debugger. Put a breakpoint on line 12. Okay, so we run the program. So now we're at a breakpoint. So the most important part is not really so much what we are doing to the structure, but where are the members inside the structure. That would be the main thing that we're going to focus on. So if I were to print here where var1 is, it is at some random address, okay, 9D, some DD 9D, okay, so just remember that. So where do you think the first member of var1 is located? Yeah, it is on the stack, but so we know where the entire structure is. It is at location DD90, or to be more precise, DD90 is the address of the first byte of the structure because the structure has multiple bytes. So if I were to ask, where do I find the first member of the structure? Where do you think that is? Same location. That is correct. Aha. All right. So this is important, okay? It is important to understand that the first member of an entire structure is at the address of the structure itself. So with that known, what do you think? Where do you think member B is located? DD9E, because it's going up, not going down, going up, and then and then C would be the next location, which is DD9F. Okay. And how many bytes do you think is var1? Or how many bytes does it use up in RAM? Should I do the Sesame Street thing, the count? Let's do that. Okay, we're counting 1 byte, 2 bytes, 3 bytes. So the structure has exactly 3 bytes. All right. This is all we need to know, okay? So once we know how a structure lives in memory, we can now define labels for the structure itself. So this way, we can also represent structures in assembly language programming, only using labels, okay? With only 2 minutes left, I'm going to kind of talk about just a little bit why do we care, okay? Why do we want to access structures in assembly language? Yes, they're contiguous. Yep. So the reason why we want assembly language code to be compatible with C code, which is what we have been doing, is because we want assembly code subroutines to be callable from C and vice versa. Okay. And then why would we want something like that? Normal people don't need that, okay? But if you need to implement really tricky stuff like multi-threading libraries and stuff like that, then you need to go low level. The only way to write code for multi-threading is to do at least a part of it in assembly language. But the other part is still in C, so you need to make sure that your assembly code can interface with C code. And that would be a main reason why we need to kind of understand all this stuff. Um, Let me see if I still have that web page up and running. We only got about 20 seconds left, but I might be able to do it. So this is on the Power Server in my account, and I think it is teachers a. It's not teachers. I think it's develops. Nope. Yep, it is. Okay, cool. I can still remember the URL. All right, so the real-time kernel, okay, this one here, this is my real-time kernel. That's why it's called DTRTK, Dr. Tech RTK. Um, it actually runs, okay? It is not a real-time kernel for TTP, okay? It is for a different architecture. This is for the architecture, the same computer architecture found on Arduinos. So the RTK, the real-time kernel itself, has a footprint of 2 kilobytes. Yes, you heard right. 2 kilobytes, 2,000 bytes. Okay, so this will even fit on some of the smaller devices on an Arduino and give that device multi-threading capability with between thread synchronization, round robin scheduling, time slicing, and all that good stuff. So this is the reason why, to me, it is important to understand how to write assembly code that are callable from C, and the other way around, also, because this whole thing was written entirely in assembly. But it also has, just regular, the interface to call that. These are the prototypes to make use of the library, but it's all in C. It's just callable in C. You have a structure. You pass two pointers to different kinds of structures, and it will do whatever this is supposed to do, which is initializing the real-time kernel. So I just want to give some context to why I teach what I teach. Okay, because it is actually useful to me. And I think this is also one of the few things that AI, there's no way you can trust vibe coding in these situations. I would certainly not do that because so many things can go wrong, and when those things go wrong, they go wrong. Okay, um, so just a little bit of context before we meet again in 2 weeks to talk about structures in assembly language programming. So that's it. So today's lab, there are two portions. So when we go to today's lab, the first portion you have to do in the lab. Most people got it done pretty quickly yesterday from my Monday, Wednesday class. So I would suspect that's the same also with this class. So the new lab is called function calls. That's just the name of the lab. And then the second portion is what you turn in next Thursday. Um, I might actually postpone this a little bit, because there's no point in turning in something when we're not meeting. So there's a program you have to write. Okay, this is the first time we actually have to write programs, write some code. So if I give you more time, I hope that will give you a little bit more time to really kind of at least give it a try and ask questions. So that's it. I don't think there's an access code for this lab. So no time limit. Okay, yeah, there's no passcode to this one, so you can just do it, anytime you want to. And then that's it. You have until 11:50 to get turn it in. And as I said, the lab itself is not terribly difficult. I think it's actually relatively easy. It's the programming side that might take you more time. All right, so I'm going to stop the recorder and